So my name is Michael Koop. I'm a graduate student at the Penn State University, and I'm working with the NanoGrav collaboration. And what I wanted to talk a little bit about today is getting into a bit more detail on what general relativity is and what gravitational waves are, and what our understanding of gravity is by looking at general relativity. I think it was 2 weeks ago, Ryan Lynch gave a talk that covered a few of the topics a little bit that we're going to be talking about, but we'll go into a little bit more detail here. And I know, at least the first time that I was trying to understand general relativity, it took a couple of goes to really get the details. So hopefully this will work out well. And please, if anyone has questions, just speak up. Feel free to interrupt me. I'm hoping that there will be lots of time at the end for questions, but if you have questions during the talk as well, you're more than welcome to speak up and ask those questions. Okay, so first, what is general relativity? Well, Einstein's theory of general relativity is basically a new way of understanding what space, time, and gravity are. So Einstein's theory of relativity has fundamentally changed how we understand the universe. And this theory is central to our understanding of what space is, what time is, and what the Big Bang is. And even some of the most extreme environments in our universe, like black holes, are described primarily by general relativity. So general relativity as a theory has made many different predictions, and every prediction that we've been able to test or observe has matched the predictions of general relativity. So it has been very successful in what it has done for us so far in increasing our understanding of the universe. However, there's still a lot that we can learn about general relativity and use general relativity as a tool to learn more things about our universe. So in this talk, basically we're going to be going over what is our understanding of gravity, space, and time, and we're going to be starting with kind of the Newtonian framework that hopefully people are somewhat familiar with, the Newtonian understanding of gravity. And then we're going to look at how Einstein changed how we understand gravity. And then we're going to look at what are gravitational waves and what can we learn from different gravitational waves. So though earlier scientists like Galileo and Kepler had studied some of the properties of gravity, Isaac Newton was the first one to realize that gravity is a universal force. It not only acts on the Earth, but it's also the things that keeps the planets in motion around the sun. So what Newton's laws do is characterize gravity as an attractive force, and this force changes an object's motion. So let's look a little bit more into detail about what this theory says. So we start with Newton's second law that you may have seen in introductory physics courses, that basically says the net force acting on an object is equal to the mass of the object times its acceleration. So basically what this equation says is that if I have different physical interactions on my system, then that can change the motion of whatever object has these forces applied to it. So if I have a block and I push on it, then there's going to be some resulting motion. So if I know what the forces on the object are, I can tell you what's going to happen to the motion. And specifically, Newton introduced this gravitational force law. This is the force between two massive objects. And this force just depends on the gravitational constant g, which is just a constant everywhere in the universe, the masses of my two objects, the mass of the smaller object and the mass of the bigger object, and the distance between those two objects. So if the objects are separated by a larger distance, then the gravitational force is going to be reduced. And these two equations together say that if I know that gravity is acting on my system, then I can plug that into Newton's second law and tell you what the resulting motion of that system is going to be. And this was extremely successful at describing many different kinds of motions. This single framework describes motions on the Earth. We get the fact that different masses will all fall with the same acceleration. If we look back at this force equation, we notice that if we set this gravitational force equal to the mass times acceleration, this part of the motion, we notice that the mass of my smaller object cancels out. All masses fall at the same rate as long as they're on the Earth and the same distance from the Earth, on the surface of the Earth. So we get equal free fall accelerations, and also this theory describes all of the motion of the planets. It explains why the orbits of the planets are elliptic, and when the orbit of Uranus didn't quite match the predictions of Einstein, or sorry, the predictions of Newton, they were able to use those differences, those errors, to predict where Neptune is going to be. The differences between what Newton predicted and what was actually seen in the orbit demonstrated that there had to be a planet farther out. And lo and behold, they look at the part of the sky where they expect the planet to be, and there is Neptune. And these predictions of Newton match the observations of the planets going around the sun and motions on the Earth to a very high accuracy. So this was a very successful theory and stood basically unchallenged for about 200 years. However, by the early 20th century, there was one observation, and only one observation, that didn't quite match Newton's theory, and this is the precession of Mercury's orbit. In the equations that Newton came up with, if I have this elliptical orbit, it should just continue in that orbit forever, and that orbit shouldn't change at all. But what was observed is that as time goes on and Mercury makes more orbits, the point of the perihelion, the farthest point out from the orbit, kept on rotating around the sun. So there was this precession motion that wasn't explained by Newton's theory. And there were a couple of theoretical issues as well, and this is going to get into a little bit of the equations, but I think it's an interesting point to look at. So let's start again with Newton's second law. We have the net force equals my mass times my acceleration. And we're going to just put this little subscript I on here because we want to think of this quantity as the inertial mass of an object. So ultimately that says, how hard is this object to accelerate? So if I have an object that has a greater mass and I apply the same force, then I'm going to get a smaller acceleration if I have a greater mass. And if I have a lower mass, then it's going to be easier to get this object to accelerate. So let's think of this inertial mass. Well, if I look at my gravitational force law, the m that we use in here can be interpreted very differently. Is there a question? I hear something very quietly, but I have the chat window open, so if you know I'm talking and you can't get my attention, just put something in the chat window and I'll see it and it'll stop. So anyway, this gravitational force law says that this quantity that we're putting in here, we can think of as gravitational mass. So how hard is it to, so this gravitational mass is more how much does this object pull on another object. So if I have more mass here, it's going to attract this other mass to a greater degree. So we have two different kinds of masses. We have how hard is this object to accelerate, and how much does this pull on a different object. And really, there is absolutely no reason in this framework why my inertial mass should equal my gravitational mass. They are fundamentally different things. One is saying how hard is it to get an object to accelerate. The other is saying how much does it pull on other objects through the gravitational force. And these two masses, this inertial mass and this gravitational mass, match to extremely high accuracy. which has been tested to, I think, greater than 1 part in a trillion, these are the same. But why is that? There's no reason in this framework as to why that should be. There are other theoretical issues as well. One question would be, is gravity instantaneous? So let's say I have the sun and the Earth is orbiting around the sun, and let's say that the sun just blinked out of existence. And if the sun all of a sudden blinked out of existence, is the Earth immediately going to leave its orbit, or is it going to continue on its orbit for a short time until some sort of gravitational signal or the light from the sun actually gets to the Earth? Because if it leaves immediately, for a small time, the sun is still shining until the signal from from the light from the sun can actually get to the Earth. So does it leave instantaneously, or is there a small delay in the gravitational effect? And in Einstein's theory of special relativity, the theory of special relativity says very clearly that there isn't even a solid notion of things happening instantaneously. So this idea that as soon as the sun disappears, the Earth should careen off in its trajectory instantaneously is a flawed idea. Another question is light going to be affected by gravity? So let's do a little thought experiment here for this. Let's say I take some mass that's up in the air, and I drop that mass. So as that mass falls down, it's going to gain kinetic energy. So with this particle, it has the mass energy and the kinetic energy. So the mass energy is from E equals mc squared, again from Einstein's theory of special relativity, but it also has kinetic energy. So special relativity says that we can convert the mass and the kinetic energy into a photon, and that photon will contain both the original mass energy and the kinetic energy that it gained. So if that photon flies back out of the gravitational field and I turn it back into a mass, well, did all of that mass energy plus the kinetic energy that it had down here, does all of that get converted back into mass? Did I find some way that I could just create energy by going through this process? And that's something that's seems to be a little bit off with Newton's theory of gravity, because photons, the particles that make up light, do not have any mass to them. So according to Newton, this photon should not be affected at all by moving out of this gravitational field. So this seems to be a way that, if that is true, we can create energy, which is, not something that we should be able to do. So here we have my favorite picture of Einstein. Always, kind of gives me the impression, don't take myself too seriously. So these are some of the issues that Einstein was considering when he tried to incorporate gravity into his framework of special relativity. So these are the questions that Einstein was looking at. But even Einstein, with how brilliant we know he was, it took him 8 years, and there were numerous times where he was trying things that weren't quite working out properly, and numerous false starts in order to find the solution. And that solution that he found is general relativity. So let's look a little bit at the kind of thought experiments that Einstein was considering when developing this theory. And Einstein was truly great in being able to do these thought experiments and gain real understanding of how the universe works from these thought experiments. So let's look at the first thought experiment that he had, the equivalence principle. So let's say I'm out in the middle of space. So we have Einstein out in space here. This is an approximate rendering of what he looked like. And out in the middle of space, we have this spaceship that's just floating out there. Okay, so Einstein's floating in his spaceship. Now, let's take another case where I'm on the Earth and I'm in a container that is in free fall. Well, let's look at these two situations and compare what the motion of particles looks like. So let's say that as I'm floating around out in space, I drop an object. Well, out in the middle of space where there's no gravity, we're not going to notice that object moving anymore. That object, if I let go of it, it's just going to float right beside me. Well, similarly, if I'm in this falling container or this falling elevator or something like that, if I take a ball and I release it, it's falling at exactly the same rate I am. So in this frame of reference, in my falling frame of reference, I'm going to see that object just staying there. So we notice that floating out in the middle of empty space and being in free fall look the same. And it's actually true that as long as this laboratory isn't too big and I'm only taking local measurements, there are no experiments that can tell the difference between whether I'm free falling in a gravitational well or whether I'm just out in the middle of space, just floating out there. So let's take a look at a different situation. Let's say I take my spaceship and I attach a rocket to it. So I'm going to be accelerating. And let's compare that to what it looks like if I'm just standing on the ground. Okay? Well, if I take an object in my spaceship and drop it, because I am accelerating, that object is going to appear to fall downwards. And the way that it falls looks exactly the same as it would look if I were just standing on the Earth and dropped an object, as long as this acceleration of this rocket matches the acceleration on the surface of the Earth due to gravity. So we see that accelerating out in empty space and standing in a gravitational field also look the same. And again, when we compare these two pictures, there is no experiment that we can do that can tell the difference between whether I'm accelerating out in space, in empty space, or standing on the surface of a planet, standing in a gravitational field. So we have these, two different sets of pictures. Now, if I was just looking at my two ships out in space, one is just in free flight, so just coasting along, the other one is accelerating. Well, if I had to decide between these two, I would definitely say that the ship that is just coasting along is in its inertial motion, its natural state of motion. And in Newton's theory, in Newton's understanding of the world, it would match that. We'd say there are no forces acting on this, I'm just floating along, I'm in inertial motion. Well, if that's the case, and we can't tell the difference between floating out in space or being in free fall, why wouldn't we call free fall inertial motion as well? This is the natural motion that an object would take. We can't tell the difference between those two, so why would we call one inertial and say that the other one is accelerating? And it is this kind of idea that is going to give us the suggestion that we want to redefine inertial motion and generalize it so that free fall is included in our inertial motion. If I'm standing on the surface of the Earth and not moving relative to the surface of the Earth, that is no longer inertial motion. This free fall is what I'm really considering as my inertial motion. So we said that if I'm in this spaceship that's floating out in space, or if I'm in free fall, any experiment I can do has to have the same results, because remember that no experiment can tell the difference between these two cases. So let's say I take a laser and a detector, and I fire a beam of light straight across the ship. Okay. Well, we said that we're going to call this straight line motion. He's out in the middle of space, not doing anything, and the light appears to be going in a straight line. So everyone would kind of agree this is a decent way to describe what a straight line is. Well, we said that the experiment has to have the same result if I'm in free fall. So when I fire my laser beam across, from the perspective of the person in this free-falling lab, that laser beam is just going to go straight across. Nothing's going to be different between these two pictures. Now, let's say we have someone watching this, this free fall experiment. So what does an observer that's standing on the ground see as the laser goes across our falling lab, and the lab is also accelerating downwards? Well, when we fire the laser, as the laser is moving across the lab, the free-falling lab, we notice that the lab itself is going to be falling, and falling at an increasing rate. It's going to be accelerating downwards. So this beam of light, from the perspective of someone on the ground, is actually going to appear to bend. Now, this is obviously greatly exaggerated. So this, for any kind of falling lab on the Earth, this would just be a tiny, tiny amount. But this kind of gives you an exaggerated look at what's happening. So we see that in this gravitational field, the path of the light that we're looking at appears to bend when we're in this gravitational field. Now, we said before that this light that's in our spaceship is traveling in a straight line. When we took this lab and put it out in the middle of deep space and it was just floating there, this experiment, we said that that's what we're going to call a straight line. So this light is actually still traveling in a straight line. But the solution that Einstein found is that this light is traveling on a straight line in a curved space-time. So this experiment suggests that massive objects can actually change geometry, can actually warp space-time. So what do we mean by mass has changed geometry? What kind of other geometries can we have? Well, in everyday life and the kind of geometry that we learn in elementary school and high school, we're used to Euclidean geometry, that is, flat space geometry. And there are all sorts of rules that we've learned and memorized about this kind of geometry. So for example, if I draw a triangle, the angles of that triangle are going to add up to 180 degrees. Okay? And also we have that if I have two parallel lines, so I have one line and two lines going through it, and it's 90 degrees, 90-degree angle between both of these lines. These two lines are parallel, and so they will never cross. These are two things that always happen in Euclidean geometry, in flat space geometry. But it turns out that this isn't the only kind of geometry that we can have. So let's look at an example of that. What about the geometry on the surface of a sphere? So let's take a sphere. You can think of this as being the Earth. And let's make a triangle on the Earth. So we'll do that by, let's say we start at the North Pole, and then we walk directly south. So we move directly south, not changing our direction at all. Everyone would agree that on the surface of this sphere, we're traveling in a straight line. We're not turning in any way. So we walk down towards the equator until we get to the equator, and we make a 90-degree turn and head straight east. And we go across the equator for a certain distance, again going in a straight line on this sphere. And then we turn north again and walk right back up to the North Pole. Well, we've walked in 3 straight lines and returned to where we started. So I've drawn out the triangle, and we notice that the angles in this triangle add up to more than 180 degrees. So this is very, very different than the Euclidean geometry, the flat space geometry that we're used to. And we also notice that these lines that we would kind of think start out as parallel actually cross at the North Pole. And since these angles are adding up to more than 180 degrees, we would say that this space is going to be positively curved. So there are other examples of different kinds of curvature that can exist, and different kinds of geometry that can exist. So we have here a space that is negatively curved. If I draw 3 connecting straight lines on this curved space, the angles in this triangle are going to add up to less than 180 degrees. And if we look at these lines over here that start out as parallel, we notice that they don't cross, but they actually diverge away from each other as we continue along these straight lines that we would have called parallel if it were flat space. So these are 2 examples of different kinds of geometry that we can have. And what general relativity says, what Einstein says about gravity, is that mass can actually change the geometry of space-time around it. So let's say I go out into deep space and I make a triangle by setting up 3 satellites and firing beams of light between the different telescopes. Okay? We're saying that we measure this triangle, and in empty space, we notice that these angles add up to 180 degrees. The normal triangle that we expect, this is flat space. Now, let's say we do the same experiment, but around the sun. Well, we said that massive objects, when we add this mass, massive objects curve light rays, and they'll curve them in this characteristic way that when we look at these angles and look at our triangle again, in this curved space-time, the angles from this light triangle that we made up add up to more than 180 degrees. This means that we have to be in some sort of curved space-time. So this kind of gives us the result that the only thing that was different between these 2 pictures is that I added mass in this one. So we see that in general relativity, mass actually curves space-time. So when we talk about this curved space-time, one thing that we often do is talk about this rubber sheet analogy. So we say that imagine space-time as this sheet that goes off infinitely in all directions, and I add some mass to it. Well, that mass is going to bend the sheet, and it's going to curve this sheet, curve the space-time around it. And then if I were to, say, roll a marble past this object, then it's not going to go in a straight line like it would before. Because this mass is here and because it's curving the space around it, this marble is going to go on a curved trajectory. So we see that space-time curvature changes the path that particles take. So in general relativity, we say that particles and light follow geodesics. That is, they're following straight lines in a curved space. And this is kind of a weird idea to wrap your head around, but there is really no better way of saying what a straight line is other than just saying it's the inertial motion that we're going through. And we said that free fall, the unaccelerated motion, just letting the lab that we were looking at free fall in the gravitational well, that is our best description of what a straight line is. So these are the geodesics that particles and light follow according to general relativity. So again, the geometry of this space-time tells matter how to move. So if we have Einstein, and again, this ship doesn't have an engine on it, so it's just coasting along. If it's coasting out in the middle of space, it's just going to continue going in a straight line forever. But let's say it were coasting past the sun, what we would notice is that the sun is going to change the trajectory of Einstein's spaceship. But one thing that we notice is that, whoops, let me go back. I seem to have changed slides unexpectedly. Okay, so Einstein flies by, and we notice that Einstein, the ship, and the ball that Einstein dropped all follow the same trajectory. They all are following along the same geodesic. So again, Einstein is going to feel no different as he swings by the sun than if Einstein was just flying in a straight line through empty space. So again, this changes our notion of what a straight line is. This motion past the sun is, the ship is still traveling in a straight line, but it's traveling in a curved space-time. So I believe 2 weeks ago, you actually, when Ryan was talking about this, he put up an XKCD comic that said, you know, we talk about this curved sheet, don't talk about the equations, that's boring. I like equations, so we're going to talk about them a little bit. Not too much, but just a little bit. So Einstein redefined what Newton's first law is. Newton's first law says an object in motion will stay in motion and an object at rest will stay at rest. Einstein changed that to particles follow straight lines, geodesics, in curved space-time. So if I were to throw a ball across the room, that is a straight line. That ball would be following a straight line in space-time, and that space-time is curved. That's why we see this apparent change in the ball's trajectory. More than that, Einstein formulated what we call the Einstein field equations. Now, in this set of equations, we see that this Einstein curvature quantity here, this represents how much space-time is curved, what the curvature of it is. And this other side, this TAB, represents what mass, what energy, what is in that space. So if I have a star in the middle of some space, there's going to be some mass and energy there. And this mass and energy changes what the space-time curvature has to be. And we notice a couple of things in here. These are all just constants. We get Newton's gravitational constant back. We get the speed of light back. And actually, what this says is that if I have energy, if I have a certain space-time curvature, that space-time curvature tells matter how to move. The matter is going to follow the straight lines in this curved space, but from the Einstein field equations, matter and energy and how that matter and energy are moving tells space-time how to curve. So this is kind of the summarizing quote from, I believe, John Wheeler, the astrophysicist. So if I have a certain mass distribution, a certain energy distribution in my space, that's going to change how space-time is curved. Now, this very much changes what our understanding of space and time are. In the Newtonian framework, space and time were just thought to be considered a set background that matter and energy move through. And it's only the interactions of matter and energy that are of any concern. Space and time are fixed. They're never changing. They're universal. But Einstein changed this understanding and said that matter and energy are actually changing space and time and the curvature of space-time. So space-time is dynamical. It's changing and interacting with matter and energy. And this is actually one of my favorite Hubble pictures. In this picture, we actually see the effect of light bending. These galaxies that are in the foreground of this image are so massive that they are distorting the image of galaxies that are behind them. And this mass of galaxies is curving space-time enough that the light from these background objects gets greatly distorted, and we get these kind of curved, wispy lines as a result of that. So we can actually see the direct effect of this curvature of space-time. Now, the rubber sheet analogy is helpful in starting to illustrate some of the important points of general relativity. So, for one, it first gives us a general sense of what we mean by saying we have a curved geometry, and it also shows a little bit that if you get closer to some massive object, the curvature of space-time is going to increase. If you're farther away from the massive object, space-time is going to look more flat, and we're going to have our normal Euclidean space if we're very far away. But unfortunately, with this rubber sheet analogy, basically everything else about this analogy can be very, very misleading. So I want to kind of introduce a few of these misleading points to avoid confusion. So the first is that space-time isn't a physical substance. It's not, there is no actual sheet out there. There's no material that makes up space-time. It's just a way, this sheet analogy is just a way that we visualize the curvature of space-time, which we live in. We live in a four-dimensional space-time. That's three spatial dimensions, the up and down, side to side, and forward and backwards, the three spatial dimensions, plus our time dimension. And this four-dimensional space-time is what's curved. So it isn't just space that's curved. It isn't just our notion of again, you know, up and down, side to side, and forward and backwards. It isn't just that space that's curved. It's the four-dimensional space-time that is actually curved. And those are two very important points, because there are other effects of general relativity that are the result of the fact that it's space-time that's curved, not just space that's curved. Also, the other common misconception is that we very often use curved surfaces to visualize these curved geometries. So, for instance, I was talking about the surface of a three-dimensional sphere is the surface of that sphere is a two-dimensional surface, and this two-dimensional surface has curvature. But the way that we most often visualize this is by having this 3D sphere, this normal 3D sphere, just saying we're looking at its surface. So we imagine this 3D sphere in a nice 3D flat space, okay? And in this 3D flat space, all of our triangles, all of the angles still add up to 180 degrees, parallel lines don't cross. We have this nice 3D space to work with, and we just say that we're only going to look at this 2D surface to look at the curvature. Well, does this mean that the only way we can have curvature is if our space-time lives in some higher dimension? Do we need some extra dimension in order to be living on this surface? And the answer to that is a very emphatic no. We can completely describe this curved geometry without ever talking about any kind of higher dimension. I can write down all of the information I need to describe this geometry without ever saying that we have a third dimension. I can just describe the surface of this sphere, and we wouldn't even call it the surface of the sphere at that point. We just say it's a curved 2D surface. So we don't need to have any kind of higher dimension, anything above the, again, the four-dimensional space-time that we live in, the three spatial dimensions in the one time. We don't need higher dimensions. And this is most often, this misconception is most often seen when talking about how the universe is expanding. So we have this picture of, we're going to imagine the curvature of the universe as living on this sphere, on the surface of this sphere, and the question very regularly comes up, well, if the universe is on the surface of this sphere and it's expanding, what is it expanding into? And the answer to that is, once again, I can completely describe the surface of this sphere and the fact that it's changing as well. I can describe that without ever referring to a higher dimension. It's not expanding into anything. This is just a way that we use to visualize it, because we are used to living in our nice flat 3D spaces. We need to use that just to visualize it, but mathematically and physically, no higher dimension needs to exist. There's nothing other than the surface of this sphere that we're looking at. Okay, so we've talked a lot about the ideas of general relativity, and it sounds, pretty far out there with, space and time curving and all of that. If someone off the street were to just, start saying space is curved, you'd probably say they were crazy. So do we actually have any evidence to back this up? Well, as we said, there was the precession of Mercury, the fact that the orbit of Mercury around the sun wasn't just staying in one ellipse, that ellipse was curving with time. The predictions of general relativity matched what the observed precession of the planet was. It also predicted the fact that light bends around the sun. So as we said, that light passing by a massive object is traveling on a straight line in this curved space, so it will appear to bend. So, and this was actually measured by, this light bending effect was actually measured by Dyson and Eddington in 1919, just a few years after Einstein developed his theory. And this was, really, this confirmation was what gave Einstein immediate worldwide recognition that this strange effect that he had predicted was actually observed and actually a real physical thing. Another example of a prediction that was matched is that general relativity predicts that clocks that are lower down in gravitational potentials run slower than clocks that are farther away from massive objects. And this is very much related to the gravitational redshift that happens when I fire a beam of light from a massive object and fire it away from that object. Then someone looking at that light is going to see the wavelength of that light increased. It will see it redshifted, and this is very much related to the fact that clocks near the surface of the Earth run slower than clocks that are farther away from the Earth. And this also was directly measured in 1959. So this was quite a while after that we actually developed techniques to measure this effect. And since these initial tests, there have been many other tests of general relativity, and like I said, many. So we have the precession of other planets, Venus and Earth. It's been matched for that. Other tests of gravitational lensing, the time it takes light to travel by massive objects is different in general relativity. Gravitational time dilation, different equivalence principle tests. All of these other tests have been matched with the predictions of general relativity. So it has been enormously successful in that no test that we've ever done has ever been against what general relativity predicts. However, even though we've done all of these different tests, there are still a few tests, there are fewer tests that involve either extremely strong or extremely weak gravitational fields. So, for instance, if I'm right near a black hole, there aren't very many black holes nearby, probably a good thing, but there aren't very many black holes nearby, so we can't as easily test the predictions of general relativity in these kind of extreme circumstances, because we really, for most labs, we just have, what's around the Earth, what's in the solar system. We can make observations of some of these systems, but it limits the number of tests that we can do. And there are actually alternative theories of gravity, alternatives to general relativity and modifications of general relativity that actually make different predictions when I have either very strong or very, very weak gravitational fields. So we want to find a way that we can test these more extreme cases, more extreme situations, and be able to determine whether general relativity is right or whether there's some other theory that might be more accurate. And gravitational waves give us a way to test these theories. So let's talk a little bit about gravitational waves. As a comparison, in electromagnetism, if I have a charge that is accelerating, so if I have that charge accelerating up and down, it will produce electromagnetic waves. In a very similar way, in general relativity, if I have certain kinds of accelerating masses, it will produce gravitational waves, and these gravitational waves propagate over the background space-time. So these waves are actually small perturbations or changes in the curvature of space-time. It's actually, you can think of it as ripples in space-time. As I look at these different areas of a curvature, if I was to do that test where I make a triangle and see if the angles all add up, that will be slightly different because there are these small curvature perturbations. And the Einstein field equations predict that these perturbations will propagate through the background at the speed of light. So that's actually one of the things that general relativity predicts about gravitational waves. And space-time curvature determines how we measure distance and time. And any changes and space-time curvature determines how we measure distance and time, and that curvature also changes the inertial motion of particles in light. So if I have a gravitational wave that would, say, pass directly into or directly out of your screen, we see this, this oscillating picture of this ring of particles. Originally, we would say that the ring of particles just forms a circle, but since this gravitational wave is passing, it's actually stretching and compressing space-time that results in this relative motion between these two particles. And this effect for any kind of expected gravitational wave source would be extremely small. This is ridiculously exaggerated. We're talking 1 part in 10 to the negative 15 is how much these particles would be moving. So the effect of these gravitational waves is extremely small. Now, one interesting thing to think about is that all of these particles, none of them are accelerating. If I was sitting on one of these particles, I wouldn't feel myself thrown from side to side like I would if I was, taking sharp corners in a car. All of these particles are following their natural motion. And the only way that we could actually determine that a gravitational wave is passing is by looking at what these other particles are doing relative to you. So the last thing that I want to say about this is that general relativity predicts that there are these 2 different polarizations of that gravitational waves can have. They can oscillate in this kind of plus configuration, or they can oscillate in this cross configuration. And that polarization thing we'll talk about a little bit more later. But the important thing is that general relativity predicts that there are only these 2 polarizations. Now, the other quality that gravitational waves have is that they carry energy. So if I were to just look at Newtonian gravity and I had 2 objects orbiting each other, Newtonian gravity predicts that these objects would continue to orbit forever. However, general relativity says that these orbiting objects are going to emit gravitational waves, and those gravitational waves carry energy. And what this will do is cause a orbital decay and the 2 objects to spiral into each other. So as they orbit each other, the orbit will get smaller and smaller, and as that orbit gets smaller and smaller, the speed increases, and eventually those 2 orbiting objects will collide and coalesce. Now, this orbital decay has actually been measured and directly observed in binary neutron stars. So we have the Taylor binary was two neutron stars that are orbiting each other. And I'm getting a little bit of feedback on Brandon's. Would you mind just muting your mic, unless if you don't have a question? But okay, hopefully it'll go away. All right, thank you. Sorry about that. So this orbital decay was actually measured. So we had two neutron stars that are orbiting each other, and as time goes on, as we observed it over a number of decades, the amount of time it took to do each orbit was gradually decreasing. And this exactly matched the predictions of how much those two objects should in-spiral due to the emission of gravitational waves. So this is strong indirect evidence that gravitational waves are physical, they do actually exist. So what kind of different systems produce gravitational waves? Well, if we have a spinning sphere, does it produce gravitational waves? No. If it's perfectly spherical and is spinning, it will not produce gravitational waves. But if I have a spinning sphere that has some sort of bump in it, then that actually will produce gravitational waves. So systems like neutron stars that have small mountains on them that are spinning will actually be a system that produces gravitational waves. If I have a mass moving just in a straight line, no gravitational waves. But if I have two masses that are orbiting each other, well, we've already used this example a lot, those two masses that are in orbit will produce gravitational waves. So any sort of binary system where we have two compact objects, it could be two black holes or two neutron stars or a black hole and a neutron star, if they're in orbit around each other, they're going to produce gravitational waves. And one thing to remember is that these gravitational waves have many of the same characteristics that other waves have. If we look at the ripples that are coming off of this object, we can identify what the wavelength of those waves are. We can define the amplitude. Those waves are going to have a frequency. They're going to have they can have different waveforms if these are evolving in some way. And as we said, these gravitational waves have polarization. And it turns out that these characteristics of what the wavelength is, what the amplitude is, and what all of these properties are determined by the system that actually produced the gravitational wave. So let's look at an example of that. This is a NASA simulation of two black holes that are in orbit around each other. So let's get that started. Hopefully it'll start. Okay. So we have two black holes that are orbiting, and these colored bands represent the curvature of space-time. So if we zoom out, these black holes are going to orbit faster and faster as they in-spiral, and far away from these objects, we see these gravitational waves that are falling away. And what happens in the middle of this is those two black holes are spinning closer together, faster and faster, and eventually form a single black hole as they collide. But what we notice, if we just watch this again, is that when they're orbiting far away, we'll just wait for it to zoom out a bit. When they're orbiting far away from each other, the gravitational waves aren't very strong and have longer wavelengths and lower frequencies. But as they come close together and spin up, the gravitational waves become more powerful and their frequency increases. So we see that these gravitational waves, depending on what their frequency is, what their amplitude is, they contain information about the systems that produce them. So if we can measure these gravitational waves, we can learn about their sources. So ultimately, we want to detect gravitational waves for two reasons. First, to study the astrophysical sources of gravitational waves. And this could be, again, compact binary systems. We can have gravitational waves from the very early universe. Possibly cosmic strings could be a source of gravitational waves, spinning neutron stars, supernovae, and maybe even some sources that we didn't even expect. But we also want to study the properties of gravitational waves themselves. So, do gravitational waves actually travel at the speed of light? Are there only two polarizations? Some modified theories of gravity predict that there could be 5 or 6 different polarizations. And are gravitational waves generated in the way that we really think they are? And this allows us to study more of the fundamental properties of general relativity and more of the properties of space and time and how gravity really works. So nanograv is trying to detect these gravitational waves by measuring the kick rate of the signals from spinning pulsars that are arriving at the Earth. So these pulsars are spinning, as most of you are familiar with this. They send a repeating signal to the Earth that acts very much like a clock, and by measuring small changes in that clock, we can try to measure gravitational waves that are flowing by the system. That was okay. Don't know what happened there again, but sorry about that. So gravitational waves will actually imprint characteristic patterns of this kind in a pulsar timing array. And the pulsar timing array is just looking at multiple pulsars to try and see these gravitational wave signatures. Now, pulsars have also been used to test other aspects of general relativity. For example, measuring the Shapiro delay. This graph might be a little bit hard to see, but what we have here is a pulsar, so that is sending a signal to the Earth, and it's orbiting a companion white dwarf. So if the pulsar just fires if the companion is on the opposite side of its orbit from the pulsar, then the pulsar signal just gets sent to the Earth and there's no real difference. There's no extra delay. But if the pulsar signal has to pass very close to the companion star, there's an additional delay that's due to the fact that, again, clocks that are near the surfaces of massive object run slower. So we get this additional delay, and this is the Shapiro delay that has been very accurately measured in pulsars in binary systems. And it is the unique clock-like properties of the pulsar that make them excellent tools for studying general relativity. And you guys, I know there are a number of members of the Pulsar Search Collaboratory and ARC here. The pulsars that you are discovering and that are being identified through the Einstein at Home project are directly helping us as providing us a tool to improve our ability to test general relativity and study gravitational waves. So this is one of the areas where your work is really contributing to our understanding of the universe. So thank you very much for your work with that, and I hope you continue with that. So that's all I have here. I hope it was somewhat interesting, and if there are any questions, I'd be happy to answer those. Just before that, I have a number of links here to the Nanograv website, our Facebook page, the IPTA website, the International Pulsar Timing Array website, the Einstein at Home project, and Pulsar Search Collaboratory and ARC. And as a shameless bit of self-promotion, I have my YouTube channel, which also has other videos kind of going into more detail in general relativity, astronomy, nanograv, and those sort of things. Are there questions? I'm happy to answer any questions.
Yes. With the bending of the light rays, would that also work with bending of other waves, such as radio waves or X-rays?
Yeah. The light deflection. Let me see if I can get the slide that talks about light deflection. So this light deflection, you guys can still see the slide, right?
Yes.
Okay. This light deflection originally was just measured by using optical telescopes and seeing the stars that are behind the sun during an eclipse. but the most accurate light bending measurements that have been done now are done using radio telescopes, I believe looking at quasars, because for the radio telescopes, you can use them during the day. You don't have to wait for an eclipse to actually do that test. So this light bending works for all frequencies of light.
Thank you.
Other questions? I should also say that I'm posting on the chat window. I'm just posting a link to the survey where we hope that if you guys don't mind, you could just kind of do an evaluation of the talk. It should only take like a couple of minutes, but after the talk, you're welcome to do that. But again, are there other questions?
I have a question. If I wanted to read more, could you suggest a layman's book that would explain more about gravitational waves and general relativity?
For gravitational waves themselves, I'm not sure how many kind of like popular science books go into that a lot, but
I was thinking of Marcia Bartusiak book. Didn't she just write a book talking about the history, like from Einstein to what we're doing now, and the building of LIGO, and possibly doing LISA and those kinds of things?
I'm not familiar with that book. I haven't read it, but it sounds like it would be a good place to look. And again, the shameless bit of self-promotion. My YouTube channel has some videos that go into a little bit more, maybe introduces stuff at a little bit more reasonable pace.
Okay, that sounds good. Thanks.
Okay, well, again, I'll be posting this on the Nanograv website and probably on my YouTube channel as well. So again, thank you guys for listening in, and hope it was good. And again, if you wouldn't mind filling out the survey, we do like to kind of get a sense of what worked, what could be improved, what topics you might be interested in. So thank you guys for listening in again.
Thanks so much. It was really good.
Okay, thank you.